Next up, evaluate the surface integral xz ds, where s is the part of the plane 2x plus 2y plus z equals 4 that lies in the first octant. Well, here we have an equation, and so we can turn this into a function, right? Z is equal to negative 2x minus 2y plus 4. That gives us that r is a function of x and y, and it equals x, y, negative 2x minus 2y plus 4. We need rx cross ry. Now, since this is a function, we can use the square root of partial of z with respect to x squared plus partial of z with respect to y squared plus 1. I don't recommend that you have to, oh, it's not that I don't recommend, I just don't say that you have to memorize that. You can, if you want to, compute this. I tell you, we're going to get the same thing that you would using that formula. So here we've got that the partial of r with respect to x is equal to 1, 0, negative 2. The partial of r with respect to y is 0, 1, negative 2. And computing that determinant gives us 2i plus 2j plus k. And so the magnitude of the partial of r with respect to x cross the partial of r with respect to y is going to equal 3. It's the same thing we would have gotten if we had gone straight for the partials. So if we had done that, it would be negative 2 squared plus negative 2 squared. That would be the partial with respect to x first, and then the partial with respect to y, plus 1. We'll get the same result. Now our line integral, or excuse me, surface integral over s was to be xz ds. And so we are going to use x is x, z is equal to negative 2x minus 2y plus 4, and our ds is dA, and so 3 from the cross product, and we'll go with, oh, what the heck, dy dx. Now that was kind of an arbitrary decision on my part. We need to figure out the limits with respect to x and y. And for that, we need to consider the region D, and D is going to be a region in the xy plane. We're going to figure out what it is by the equation of the plane that we were given. Z equals 2x plus negative 2x minus 2y equals plus 4. Now, you know what? We're going to use this one. 2x plus 2y plus z equals 4. We're going to let z be 0. If z is equal to 0, then we have x plus y is equal to 2. So this is a region in the xy plane. X plus y equals 2. And so this line here is going to be y equals 2 minus x. And so y is going to go from 0 to 2 minus x. And x is going to go from 0 to 2. So y goes from 0 to 2 minus x. X goes from 0 to 2. And we have this nice integral to compute. I will leave it to you to verify that the answer is 4. Now, folks, we made a decision early on here. There was the equation of the plane 2x plus 2y plus z equals 4, and I immediately solved for z, thereby projecting d onto the xy plane. We could just as easily have projected onto the xz plane. Starting with 2x plus 2y plus z is equal to 4. We could have had that solve for y. Y is equal to 2 minus x minus 1/2 z. Now, I'm not saying that this is a better way to go. I'm just saying we had alternatives. I probably went for z because it had no coefficient of 1. But we can deal with this in terms of x and z. Y is a function of x and z. So in this case, we would have r of xz is equal to x 2 minus x minus 1/2 z, z. Now at this point, we could either take the partials of r with respect to x and then z respectively and form the cross product, or go back to the equation we have y equals 2 minus x minus 1/2 z and use that square root formula. And I'm going to go for that this time. partial of y with respect to x squared plus the partial of z with respect to x squared plus 1 is equal to the square root of, now the partial of y with respect to x is -1. So inside the radical, -1 squared. The partial of y with respect to z is -1/2. And so -1/2 squared plus 1. Result there is going to be 3/2. And you say, well, that's a different value than we got before. We had 3 before. Yeah, I know, it's true. And we also have a different region in the xz plane. Letting y equals 0, we end up with z equals 4 minus 2x. So our integral, surface integral over S of xz ds then becomes the integral. Now z goes from 0 to 4 minus 2x. X goes from 0 to 2. Our integral is, the integrand is simply xz. And then ds gives us this 3/2, and we had decided dz dx. The intermediate result is that we have a simpler integral to compute. The net result is the same answer of 4.